All right, so this is the first of two videos on chemical equilibrium. We're going to look at the first 16 or so slides in this video, and then we'll look at the second set of slides in the second video, part two. So if you're looking for part two, head over there. All right, so what is equilibrium? Well, we've talked about equilibrium a couple times. We've mentioned it. We even had a brief discussion of Q and K back a few units ago. But now let's really look at it. So chemical equilibrium is a state where the reaction in the forward direction and the reverse reaction are occurring at the same rate. And a really common way that we demonstrate this is with dinitrogen tetroxide, that N2O4 there. And as a frozen, like in a really cold environment, the N2O4 forms a nice colorless gas. And when it warms up, all right, when it's frozen, it forms a gas. Geez. When it is frozen, it is a colorless solid. As it warms up, it turns this kind of brown NO2 as it dissociates. And if you keep warming it up and allow it to reach an equilibrium, then it will give you that nice dark brown. All right, and that's something that we usually kind of use as a demo. So we can take it, put it in warm water, put it in cold water, and watch the color change. So obviously we know that temperature can affect rate, all right, and that rate can then, result in different colors. Now, when a system is approaching equilibrium, the forward and the reverse reactions are both occurring. So this is the region. Whoa, where's my pen? There we go. This is the region where we are approaching equilibrium. This is the approach. And you can see that as time is progressing on the x-axis there, that the reaction is occurring in both directions, okay? Now, to us as the observer, it appears that the reaction is only moving in one direction, but both are actually occurring. At equilibrium, which is this dotted line, equilibrium right there, that's the dotted line. That's the point where, to our eyes, right, the reaction appears to cease. But what is actually happening is the forward and reverse reactions are occurring at the same rate. So what we observe is no net change. And that means that the amount of reactant and the amount of product is going to remain constant as time continues on. Now, it doesn't matter which one of these two graphs we look at, all right, whether you end up in this case with more NO2, or if in this case you end up with the same, or when you're looking at rate, when the rates flatten out or the concentrations flatten out, that's when you know you've reached equilibrium. So after this dotted line, or that dotted line, because my slope here is a flat line, it's flattened out my curve there, I know that I've reached equilibrium. So how do we write equilibrium? Well, you probably already know this, but it's worth pointing out. We use the equilibrium arrow. I mean, it's pretty self-explanatory. And remember that when we're talking about equilibrium, we're actually describing rates. And so if we look at the N2O4 example, where it's converting from N2O4 gas to nitrogen dioxide gas, here's the rate law right there. There it is. The rate constant is going to depend on the concentration of N2O4. Now, for the reverse reaction, it's going to depend on the concentration of NO2, and it's squared, right, taking into account the stoichiometry there. And the thing that you might see here is K sub F for forward and K sub R for reverse. And it should be pretty obvious that at equilibrium, the forward reverse and the and the rate of the reverse reaction, the forward rate and the reverse rate are equal to one another. Now we can rearrange that, all right, and get K on one side, and we'll find that if we solve for this, we get a constant, and we call that constant KEQ, all right there. So let's look at a real process. Let's look at the Haber process, one that we use industrially. This is one that you'll see in your textbook quite a few times. You probably see it on the test. Wouldn't surprise me at all to see it on the AP test. It's a pretty common test item. And the reason for that is it's got some stoichiometry associated with it because the coefficients aren't all one. So when I look at the Kc, right, my equilibrium statement here, I can see I have my products on top, I have my reactants on the bottom. And when we think back to the equilibrium constant as a whole, we remember that the products go on the top, the concentration of the products raised to their coefficients, right? There's the coefficient, the little lowercase letters in this generalized equation, and the concentration of the reactants and raised to their coefficients go on the bottom. Now, it's worth pointing out that if we're talking about concentration of gases, that there is an equilibrium expression for, or in terms of pressure. And so you can relate these two things using PV equals nRT, right? The ideal gas law that we learned last year. In the ideal gas law, when you start to rearrange some and get pressure by itself, you end up with N divided by V. And number of moles divided by volume is concentration, right? If I put moles over like liters, that would be N over V. And so that is a concentration value. And so with that kind of or with that substitution in mind, there can actually be a statement written that relates Kp and Kc. So in terms of concentration or in terms of pressure. So that is a very useful equation to know. I think you guys obviously know what delta means. The delta N is talking about the product minus the reactant, though, in this scenario. So just make sure that you're aware of that. But anyway, that is a very useful equation. And in case you need to convert between Kc and Kp. Back to equilibrium. So you can reach equilibrium from either direction, all right? It doesn't matter if you're reaching it, it doesn't matter how you change the concentrations, you can still reach the same equilibrium either way. So in this experiment here, we started with 0.04 up top, and we started obviously at 0 at the bottom because we hadn't made anything yet. But it doesn't matter what our initial concentration of N2O4 is, we're going to reach the same ratio in the end. So when we're looking at a specific chemical process, that ratio is not going to change. And when we look at K as a number, there's two conclusions we want to be able to draw. Number one, if K is really big, then we know that the equilibrium is favoring the products. And a lot of times we'll write that arrow like that. We'll have the bigger arrow pointing towards the products. Now, if K is a lot smaller than 1, well, then we're favoring the reactants, right? And sometimes we'll write that arrow like that. So if you see one of those arrows, it's not a big deal. When we describe it, we say lies to the right or lies to the left. That is assuming, obviously, that the reactants are written on the left and the products are written on the right, just like we would write a sentence, right? We read left to right. When we look at the forward and the reverse rate, right, and we want to maybe flip Kc because we want to talk about the reverse of a reaction, you need to be aware that that means we have to take the reciprocal of the equilibrium constant. So in this forward reaction of N2O4 reaching equilibrium with 2 nitrogen dioxide, this is our equilibrium constant. If I want to flip the reaction around, right, which I've done here, then I have to take the reciprocal of that value, which gives me an equilibrium constant of 4.72. In a similar vein to Hess's law, where we can put different compounds or different equations together and manipulate some of the values that go with them, some of those measured values. If we start to increase the number of molecules that are involved, so let's say we want to double the reaction, then we raise the original equilibrium constant to that power. So if we, double everything from equation 1 to equation 2, then we're going to obviously raise that to the power of 2. We're going to square it. Same thing if we wanted to, triple it, we would cube it. If we want to, multiply by 4, we'd raise it to the 4th power. So that saves us from having to do a whole lot of extra maths. Now, if you have two equilibrium constants for unrelated equations, and then you put those equations together, so I have equation A, equation B, and then I've put them together to make equation AB of some other reaction. Well, the equilibrium, the new equilibrium constant is the product of the starting uh, equations there. So I take K1, I multiply by K2, and that's going to give me K3, my overall equilibrium constant for this new reaction. Now, just to kind of finish up, it is worth pointing out that there are two different kinds of equilibrium. There's homogeneous equilibria, in which case the reactants and the products are all in the same phase, so like they're all gases or they're all liquids or they're all solids, whatever. There's also heterogeneous equilibrium, which occurs when something in the equilibrium expression is not in the same phase as the rest. So something to keep in mind, all right, if you're talking about a pure substance when it comes to equilibrium, is that the value we use for concentrations of those pure substances is always 1. You're going to see that a couple times in your homework. Now, here's a great example of a heterogeneous equilibrium. So this is the decomposition of calcium carbonate, which is a solid, and it breaks down into calcium oxide and carbon dioxide. So that's going to produce a solid and a gas. And so we can see that we don't have everything in phase here, but we do have an equilibrium arrow. Now, when we talk about a pure substance, that's CaO, that would be where I would use my concentration of 1, because that's considered to be a pure substance, right? It's a solid. So that's the end of the first video. If you have any questions, let me know. In the second video, we'll look at ice tables and do a little bit of math here.